an introduction to the material, and something you definitely need to be doing. This became clear to me in my last period geometry class. You need to know what some of the terms are and what's, like you need to know, for example, what the segment addition postulate is, right? There's not a ton of stuff in this chapter that you gotta know, but there are some things. And so over the next few days, you're definitely gonna wanna go back, maybe click through the PowerPoints quickly, if you feel like that's something that would be helpful. Take a look at the book, or if you're just looking at the PDFs of the book, either one, they're the same thing. Look through those, maybe glance at a couple of examples, but for sure, look at the important parts of the book. The book does a pretty good job. It's a really old book, and it's, I'm sure there are some complaints. It's not exactly the book I would choose, but it does do a good job at certain things. And one of the things it does is, like, vocabulary is always sort of highlighted. When you see one of those green boxes in the book, those are the important things, right? The postulates. Make sure that those make sense to you, right? Those are going to be things that's vocabulary that I'm going to expect that right? So make sure that you're keeping up on that. The book assignments are kind of our first look at this stuff, but a better and more important look is going to be the review assignment. Review assignment is probably the most important thing that we do, even though it's only one assignment. It's probably the most important thing we do each chapter. The review assignment is going to have some questions that are going to be very similar, but some of them that are going to be, I think, a little better. Some of them are going to be maybe more geared towards what I think, based on the research, are the kinds of things that you need to know to succeed at the next level. So, for example, there's going to be more stuff on the review that's going to be kind of algebra based. And I want to just do a quick run through of 2 problems, just to remind you how that works, and then I'm done for a while. Then we'll go to the lab. You've got the stuff to work on. This is a pretty big class, but you guys also have been doing a really good job. I've been very impressed with this group. Seem to be doing a good job of getting questions answered, of using the lab time. Make sure when we're in the lab, take advantage of me while you've got me there, right? I mean, really, I want to be answering questions constantly in the lab. That's my goal, is that I've always got people asking me stuff so I can be helping you through places where you've got some issues, right? Okay, so having said that, let's take a quick look at a couple problems. These are the kinds of problems. Is it better? You tell me, is that better or is that better? That's better, okay. So problems like this. Now, this is one that's geared towards the segment addition postulate, right? They're telling us here in this problem that n is between m and o. Well, what do you suppose those are when they say n and m and o? Points, exactly. Those are points, aren't they? So point n is between m and o. So that's a very specific picture in geometry. What does that look like if n is between m and o? So if this is point m, for example, and this is point o, can n be down there? No, can't be. It's got to be, in fact, it has to be on what? Good. It has to be on the line connecting m and o. And it's got to be, it can't be out there, can it? No. And it can't be out there, right? It's got to be someplace in here. So for example, how about right there, right? Okay, the other thing we've got to know here, we have to remind ourselves of, is what does it mean when we say something like that? If I say mn and there's no symbol on top, what is that representing? Yes, Carol? It's a distance, yeah. It's the length of the segment or the distance, right? So when we say something like this, we know that mn is the length of that. Now, what's that? Segment mn. Sure, or another way of saying it would be the distance between the points m and n. Same thing exactly, right? Okay, good. So then if that's what, so this is the distance between m and n. NO represents the distance between n and o, and MO represents the distance between m and o. So the segment addition postulate then tells us what about those 3 distances or lengths? How are they related? What has to be the case? What do you think, Kristen?
8x minus 14 plus x minus 1 equals 11x minus
Okay, now I'm gonna jump back one step from that. That's what we're gonna come to. But for right now, all I want is just the geometry relationship. We're not gonna worry about the algebra yet. But the way I want you to think about these is first we're going to try to come up with a geometry relationship, and then we can harness that geometry relationship to maybe solve for a variable. Because if we're trying, look at the questions that we're being asked. We're supposed to find the lengths of each of these three segments, right? So we've got to be, in geometry mode, we've got to be thinking, okay, well, how are those three lengths related, right? And that's the segment addition postulate, right? So, Nick, what is the segment addition? You finish this for me. The segment addition postulate tells us that the length of segment MN plus
The length of segment NO equals the length of segment MO.
perfect, right? That's it, right? So this length plus that length equals the whole thing. It makes sense, right? That's the segment addition postulate. If N is between points M and O, then that always has to be true, right? So that's the geometry relationship. Now here's where this is still a little bit new to you, but this is the kind of problem that pays dividends down the road in Algebra 2, right? So I've got to somehow, if I want to know what those lengths are, they're all written in terms of the variable x. So I've got to know what the value of x is to be able to plug that in, right? So this is where I've got to take that relationship and build an algebra equation out of it, right? So, and that's what Kristen gave us. So that's going to tell us that, well, the length of segment MN is that expression, right? So that's going to be 8x minus 14 plus the length of segment NO is just x minus 1, and that's equal to the length of segment MO, which is 11x minus 21. Okay, now we can shift out of geometry mode for a while, and we're just doing algebra, right? We're just doing algebra. So Shaw, what am I going to do with this equation, do you think? I've got this equation here.
Combine like terms.
Combine like terms, great. So on the left side, 8x plus x is 9x, good. Negative 14 plus negative 1,
Negative 15.
good. Negative 15, good. So that's equal to, on the other side, we've just got an 11x minus 21, right? Good, good. Brady, what am I going to do? What do I do next here then? Great idea. Let's push the x's to the side where we'll have a positive amount of them. That makes things a little bit easier. So we'll subtract 9x from both sides, and that's going to give us, those cancel, so I'm going to get a negative 15 equals, what's 11x plus negative 9x? 2x, good. Minus 21. Next step, Maria, what do you think? Say it again. Okay, we could, but now I want you to think ahead here just a little bit. Our goal is to solve for x, right? So yeah, so what are the steps going to be to get, so maybe you want to change your answer. Add 21, good. So if we add 21 to both sides, that's a good idea. That gets rid of those, and then what's the last step? Then I just end up on this side with 2x, and what do I get here, 6? Negative 15 plus 21. Last step, divide by 2, perfect. So then we get x equals 3. Now, that's our algebra answer, right? But it's a geometry question. So we've got to take that x equals 3, and now we got to go back up here and say, okay, well, if x is 3, I need to answer these geometry questions. How am I going to do that? Plug it in. Exactly. Plug it in. Right? So I'm going to plug in a 3. Whoops. I'm going to plug in a 3 there, and there, right? And get numbers. So what is 8 times 3? Minus 14? 10. Yeah, it's 10, isn't it? What is 3 minus 1? 2. 3 times 11? 33 minus 21? 12, yeah, it's 12. So it works, doesn't it? 10 plus 2 equals 12. We got it. Okay, make sense? And now we're done. Now we answered the geometry question. Okay, so here's the part. You guys are, I'm not going to let you off that easy, though. A lot of the algebra you're going to be doing from this point forward involves stuff like this. Now this is, for now, this is going to look a little scary, but by the end of the year, these kinds of things will be nothing, right? Let's walk through this one together, though. You'll see it's not as scary as it looks. So here's our situation. We've got these we want to know what the measures of these three angles are, right? The measure of angle EWL, well, isn't that just this angle? That's just this angle right here, isn't it? Right? We want to know the measure of that angle. We want to know the measure of angle LWT. Well, LWT is just this angle, right? And then it wants to know the measure of the great big angle, EWT, which is the whole thing. What's the geometry relationship that's going to relate those three angles? Okay, good. Does everybody agree? So let me restate that. I'm going to say it without, it gets confusing when we say all the, it's just going to be this small angle down here, right? Plus the small angle up here equals the whole thing, right? Anybody remember the postulate that tells us that? Angle addition postulate. Remember, all the angle addition postulate says is just that if two angles share a vertex and a common side, that just means they're adjacent angles, right? So then their sums must add up to the sum of the big angle, essentially, right? In so many words, that's all the angle addition postulate says, right? I think it says actually more precisely, if we have a point on the interior of the big angle, then the two small angles that it creates add up to the big angle. But same thing, right? It's just I don't care if you remember the specifics. You're going to forget those. I just want you to remember the idea of what it means, the angle addition postulate. So once again, look, all of these angles are given to us in terms of x's, right? So we're going to have to solve for x to be able to answer the geometry questions. Okay, so, but we have the relationship. We know that this small angle plus that small angle equals that big angle, right? That's our geometry relationship. So what does that give us then? So we're going to get, I'm going to put this one by itself on the left side this time. Just doesn't make any difference. You understand that when I have an equation, it doesn't matter which part of the equation I put on the left and the right. I can switch those, right? Easy to do, right? So this is going to be my geometry relationship. I'm going to say that the measure of the big angle, EWT, equals the measure of the bottom angle plus the measure of the top angle. And I could have put those on either side of the equation. It makes no difference. So what are those expressions? Okay, the measure of EWT, this one, is just x plus 76. EWT is, oh, that's supposed to be an L, isn't it? Whoops. Yeah, let me fix that. Whoops, I wrote that wrong. That's supposed to be an L. There it is, right there. So that's going to be negative 3 x squared minus x plus 183. Why are there squares? Because I put them there. That's okay though, right? We're just going to get an equation that's a little bit different. In the last example, our equation was linear. It didn't have any x squareds in it, right? But we just had to solve it and figure out what x was. And this is a little harder. In this one, we're going to get an equation that does involve x squareds. And so solving it's going to be a little bit different and probably a little more complex. But I'll remind you how to do that. Okay. For now, I'm not going to give you any, on the review or the test, I'm not going to give you any really hard ones involving quadratics. They'll all work out nicely for now. As the year progresses, we'll kind of make these more advanced. But for now, trust me, they won't be bad. The measure of angle LWT, well, that's that guy right there. So it's 2x squared minus 3x minus 93. So we're in the same kind of boat. Last time Shaw told us to combine like terms. Again, that's what we're going to do, right? We'll combine like terms. On the left side, we've just got x plus 76. What are we going to get here? Let's add up like terms. Negative 3x squared plus 2x squared. Those are like terms because they have the same powers of x, right? So what do those add up to? Negative 3x squared plus 2x squared. It's just negative x squared. Good. Okay, so let's kind of cancel them out as we go. So those two we took care of. What about negative x plus negative 3x? Negative 4x. So we combined those, done with those. And then positive 183 plus negative 93? 90, good. Okay, so we took care of those. So all the terms have been combined. That's where we stand. All right, now this is the part that's different though. This is where we have to kind of, and you've done this before, and we even did this a little bit during the algebra review, but definitely this is something, pay close attention to this, because this you may not be as fresh in your minds. When we're going to solve an equation like this, it's a little different. When I've got an equation that has both x squared and x's, I can't just isolate x, right? Like we did in the last example. Okay, I've got to do something different. And the something different I do is I want to get all the terms on one side and set it equal to 0. That's what we call standard form. Okay. We want the number of x squareds to be positive. So the coefficient of x squared needs to be positive. So on which side should we push everything? To the left, right? Because right now we've got a negative number of x squareds. So we're going to add x squared to both sides. We're going to add 4x, and we're going to subtract 90. Okay, and if we do that, what happens? So all these guys cancel. So on the right side of the equation, we're just going to get a 0. Now what about the left side? Well, I've got an x squared that's just by itself, so I've got there's my x squared. X plus 4x is 5x, and 76 minus 90 is, what, negative 14? Okay? So there's our, now you don't have to remember this for now, but this is what we call a quadratic equation in standard form. And that's what we need. Now, do you remember back? I want you to think back to the beginning of the year. I went through an example with you guys. I told you we were going to do a warm-up, and I had you multiply all these bizarre numbers together. Told you to keep track of all that, right? And it seemed impossible. Then I multiplied by 0. And what was the answer? 0. Okay, the moral of that story was that the only way you can multiply stuff together and get 0 is when you multiply by 0, right? And so here's a great trick. Here's our trick. Instead of trying to just find values of x that are going to somehow make all three of these terms add to 0, that's impossibly hard to do. We're going to try to break this apart into a product of two really simple factors that we can set equal to 0 and solve easily. And that's why we spend so much time factoring at the beginning of the year. So this is an easy kind of factoring problem because there's a 1 in front of the x squared. So we always call these the easy kind. This is not a bottoms-up one, right? All we have to do here is just kind of fill in the blanks, right, if it factors. So what do the magic numbers in this case have to do? Because all I have to do is find the magic numbers and I've done factor. What do they have to multiply to? Negative 14. Good, they're going to multiply to C and they're going to add to B, add to 5. So what are those numbers that multiply to negative 14, add to 5? What are they? 7, what are the signs going to be? It's positive 7, negative 2. Everybody agree? Positive 7 and negative 2 multiply to negative 14 and add to positive 5. So I get x plus 7, x minus 2. We got it factored, right? Now here's the trick though. This is a great strategy. So we know that the product of those two factors can only equal 0 when one of the factors is equal to 0 itself, right? Those are easy equations to solve. That's what we call the zero product property. You can only have a product can only equal 0 when you're multiplying, when one of the factors is 0. So there's really two things that could happen there, right? Then either, you might remember talking about this. So either x plus 7 has to equal 0, so we can get 0 times something equals 0, or x minus 2 would have to equal 0, so we get something times 0 equals 0. Well, what are my solutions going to be? These are easy to solve. What's the value of x in this equation if I solve? Negative 7. So that's one mathematical solution. What's the answer to this one? 2, okay? There you go. So I get 2 answers, 2 values of x. Well, that seems like a problem. However, what's frequently going to happen in situations like this when we're solving these quadratic equations is the math gods are going to give us one solution that works and one that doesn't work, one that doesn't make sense in the context of our problem. Remember, our problem is not an algebra problem. It's a geometry problem, right? So let's try out the x equals 2 and see what that does for us. If I go back up here, and I'm just going to quickly grab this guy right here. Oh, come on. There we go. So let's try this one. Now, if we pick, if I pick x equals positive 2, what am I going to get? Well, this one's going to be, would you agree, if I plug that in, I'm going to get negative 3 times, instead of an x, I'm going to have a 2, right? Negative 3 times 2 squared minus 2 instead of an x plus 183. Well, what's that going to give me? What's 2 squared? 4. So I'm going to get negative 3 times 4 is what? Negative 12 minus 2 plus 183 is negative, so what's that going to be? 169 degrees. Okay, what about this guy here? What's it going to give me? I'm going to get 2 times 2 squared minus 3 times 2 minus 93. Well, 2 squared is 4, 2 times 4 is 8, right? 8 minus 6 minus 93. Uh-oh, something weird's happening. What am I going to get for an answer? I'm going to get some negative number. Does that make sense? No, not in the context of our problem. That doesn't make sense, does it? So what does that tell us about the solution x equals 2? It doesn't work. Right? So if we go back here, we can say we know that this one, that one didn't work. Let's try negative 7. See what happens with negative 7. Let's make this a little quicker. Somebody have a graphing calculator handy?
Mr. Roy?
Yeah.
I'm really sorry, but can I go to the bathroom?
Yeah, absolutely.
Yeah.
Okay, so what's this guy going to give us now? If we have x equals negative 7, okay, what's the top one going to give us? Let's plug this in. So I'm going to get negative 3, focus, times x is negative 7, right? So I'm going to take the quantity negative 7 squared, that's my x, minus negative 7 plus 183. Well, what's that going to give us? Negative 3, what is negative 7 squared?
Negative 49.
No, positive 49. A negative, any number squared is positive, isn't it? Because a negative times a negative is positive. So I'm going to get negative 3 times 49. What's minus negative 7 equivalent to? Plus 7 plus 183. So we'll just do this quickly. So that's going to give us minus 147 plus 7 is minus 140 plus 183 is positive 43. And you can just do that on your calculator. I just want to go through it quickly so we can see what happens. What about this middle one? So the middle one is going to give us 2 times negative 7 squared minus 3 times negative 7 minus 93. Well, that's equal to 2 times 49. Negative 3 times negative 7 is positive 21. So that's going to give us 98 plus 21 is 119, minus 93 is 26. Okay, and you can do it on your calculator once again. The bottom one, down here, we're just going to get negative 7 plus 76 equals 69 degrees. And what do you know? It works, doesn't it? 43 degrees plus 26 degrees equals 69 degrees, right? So those are our answers. Make sense? Isn't that great? Okay, off we go. Let's see. We're going. Let me tell you where we're going.